start right here at the top of our page. We are going to be graphing a function that we are very familiar with. So we've already done some work with this one, f of x equals 2 to the x. Now, I want to remind you that there's really an invisible 1 out in front of this, and so if we were to think of it in the format of y equals a times b to the power of x, it's kind of like a is 1. And so if we wanted to connect this with a story, which is something that we did a lot of on the very first day, something starts with 1, and then it's continually multiplying by 2 every time period. So it might be every week, or every month, or every year. It's doubling. And so in the context here of this table that we're wanting to fill in, there's a couple of ways that we can think about filling it in. Whatever the starting value is, in this case our starting value is 1, that is always going to be when x is equal to 0. If x is our time period, if it has been 0 days or 0 weeks or 0 years, that's where we're going to start. And then the meaning of the 2 is our growth factor. That means every time x increases by 1, or like you add 1 day, the duckweed plant, for example, the area is going to double. Add another day, the area doubles again. So that's one way that we can think about filling values into our table. Now, another thing that we can do is we could simply plug them in. So if it's y equals 2 to the x, well, if x is equal to 0, 2 to the 0 equals 1. So that would be this one. 2 to the first power is 2. 2 to the second power is 4. So what we're doing is we're just taking the number across the top row. In the x row, we're just plugging that in for x, and we're evaluating it to get the answer for y. F of x here is another name for y. All right, so if we were to keep going, either doubling or plugging the numbers in, when x is 3, we end up getting 2 to the third power is 8. And then thinking about doubling, that can help us with getting 2 to the fourth power, which is 16. All right, so we filled this in for all of our positive exponents. There's one that we still need to do at the start, and that is when x is equal to -2. So a couple of ways you can think about this. Every day moving forward, the duckweed plant doubles and multiplied by 2. So if we were to move a day backward, the area, the amount, would divide by 2. And actually here, because we've gone backward 2 days, we're going backward 2 steps, it would be dividing by 2 twice. The first time it divides by 2, it's going to turn into 1/2. When you divide that by 2, it's going to turn it into 1/4. So we could think about dividing by 2 twice. Another thing that you can do here is we can just plug in the negative exponent. 2 to the -2 is the same thing as 1 over 2 to the +2. So you'll notice that we get exactly the same answer of 1/4. Continuing to plot these values here from the table, we've got 2, 4, and then we have 3, 8. All right, and let's go ahead and connect those points with like a smooth curve. We know that it's going to go onward and upward on the right. On the left-hand side, we know that it's going to flatten out to make kind of this tail that looks very flat. It's getting close to the x-axis, the horizontal asymptote, but it's never going to actually touch or cross over. In fact, let's also go ahead and show the asymptote as a dotted line. We'll do that right on top of the x-axis. All right, and from the information that we've done so far, again, this is a little review. We've seen it before. We're going to fill in these questions about y equals 2 to the x. Now, when it says intercept, this is referring to our y-intercept. We actually don't have an x-intercept on this one, right, because it's never touching the x-axis. So the y-intercept is 0, 1. Remember, our domain is asking what are the x's that are used in this graph, and we said it was all real numbers. All of the x's are represented here on the graph. Another way to think about domain is what type of x values can you plug into the equation? You could plug any x value in. You could plug a positive number in. You can plug a negative number in. You could even plug in a fraction. We talked about that at the start of class today. It's just going to turn it into some type of root, and that's all okay. So our domain is all real numbers. Now the range is asking, what are the y values that are possible to come out of this function, or what are the y values that are represented here on the graph? And we only have y values that are positive. We only have y values above 0. We don't have any y values down here in the negatives. And so a couple of ways you can write this. You can say y is greater than 0, or you can say the range is all real numbers greater than 0. We just have to know and remember that the range is talking about the y values. All right, now for the asymptote, it is a horizontal line. Anytime we want the equation for a horizontal line, we're going to write it as y equals a number. The y value that that horizontal line is passing through is the y value of 0. So it's going to be y equals 0. And actually, I'm going to make a little note down here below that this is a horizontal asymptote line. All right, so we've done 2 to the x. But really, our focus for today, what we're actually interested in, is the inverse. And so when you take a look at the equation that's written off to the side here, g of x, that is log base 2 of x. This is the inverse of 2 to the x. They are actually inverses of each other. And one thing we know about inverses, we talked about this briefly yesterday as well, is that it's all about switching the x and the y values. So if I were to identify just one point here on the graph, actually, let's do 2 of them. Let's look at 2 of them together. So I'm going to start with this one over here. The ordered pair for that point is -2, whoops, go away, little line. It's -2, 1/4. If I were to switch the x and y, it turns into the point 1/4, -2. Well, let's think about where that would be plotted. 1/4 is a little bit to the right of the y-axis. It's only like 1/4 of a square over to the right. But then -2 is down here. So this is what that first point is going to look like. And I'm going to label this 1/4, -2. All right, let's take a look at changing the next point. So the next point here, we have our intercept, our y-intercept 0, 1. Well, when we switch the x and the y for the inverse, it becomes 1, 0. So it actually turns into an x-intercept, 1, 0. All right, and we could continue the process from there. So what I would like you to do is go ahead, I'd like you to write out what are the ordered pairs, the rest of them, on the blue line. Think about switching them to turn it into the inverse, and go ahead and plot them where we started plotting the red points. Then I want you to connect them in the way that looks like it would make sense. That new graph is the inverse graph for log base 2 of x. And then once you have that graph done, I want you to go ahead and fill in these 4 answers. And check it. Okay, so I continued by, again, just thinking about what were the ordered pairs here on the blue line. So this is for the original graph of 2 to the x. Every time we just switch the x and the y. So the next point on the blue line was 1, 2. When we switch it, it becomes 2, 1. The point 2, 4 becomes 4, 2. And then the point 3, 8 becomes 8, 3. Now what happens when we connect these, if we start at this first point that we did, we can see that this one also has a little bit of a curve to it. It's going to continue like onward and outward to the right. But what happens as we get to the left, it's going to get closer and closer to the y-axis, but it's never going to actually touch or cross the y-axis. So it's just the opposite of this one getting closer to the x-axis. We had a horizontal asymptote here. When all the x's and y's get switched, that asymptote also switches, and so it's going to turn into a vertical asymptote. If you haven't already, I'd like you to draw a dotted line on top of that y-axis to show that this is going to get closer, but it's never going to actually touch. So it's going to be a tail, but it's going to be like very straight. It's going to look very, very vertical. So when we take a look at how we have filled in the other pieces, notice how everything has just switched. The intercept, the y-intercept, becomes an x-intercept because 0, 1, when you switch the points, it becomes 1, 0. So we used to have a y-intercept on the graph of the inverse, on the graph of log. It turns into an x-intercept. Now, let's look at what's happening with the domain and range. Domain is still asking, what are the possible values for x? Well, on the log function here, first of all, we can see on the graph that we don't have any negative x values because this line is never crossing over the y-axis, like it's never getting into the negative. We only have positive x values. And remember at the start today, we said you can't take the log of a negative number. So if the x's represent the numbers that we're plugging into the log function, we couldn't put a negative in the log function anyway. So our domain is now only real numbers greater than 0, only positive. Now when we look at the range on this one, now there's no limit to what the y values could be. This is going to go onward and upward forever to positive infinity. Up there for the y values, that arrow that's pointing down is going to span all of the negative y values going downward. So in that y direction, we have no restriction. So now the range is all real numbers. So what I want us to notice here is that the domain and the range, they just switch between the original function and its inverse. So we go right off to the side. Not only are we switching x and y, we're seeing that the domain and range also switch, which makes sense because, after all, domain describes x's and range describes y's. If all the x's and y's switch, wouldn't the domain and range also switch? And then the way that we're going to write in the equation for our asymptote, this vertical line here, anytime we want a line that's vertical, we have to put an x equals in front of it. This time it's x equals 0 because 0 is the x value that it's passing through. So notice that within the asymptote equations, x and y, they switch places again. All right, so this is the idea of what's happening with our original function 2 to the x and the inverse, which was log base 2 of x. There's one last thing on this picture that I want to show you. And we've actually seen it before. So we saw it back in chapter 6 when we first did inverses. This is kind of a cool picture to see it happening again. There's a special kind of reflection that happens between a function and its inverse. If you can draw in a vertical line, a diagonal line where I have put this green dotted line, what that line is representing is it's representing the equation y equals x. It's the most basic linear equation that has a y-intercept of 0, has slope of positive 1. And remember, something that we saw before is that a function and its inverse, the graph, will be reflected over the line y equals x. So that means if I were to fold my paper over that green line, the blue curve is going to perfectly match up with and align with the red curve is going to match up. So that's always something that's true for the graph of a function and its inverse. They're always reflected over the line y equals x. This is already. The part that we can take a look, though, at filling in is question number 3. So we started by doing a table for 2 to the x. We did that at the start. And in question 3, we're looking at how could we fill in a table for g of x, filling in a table for log base 2. And so we have talked about some of these ordered pairs already on the graph when we were just thinking about switching the x's and the y's. And so we saw up here on the graph that like when x was equal to 8, we saw that it had a y value of 3. Another thing that we can think about that is if we were to plug the value in, 8 for x, it's going to look like evaluating logs, which is what we did in class yesterday. So we could also get it like this: log base 2 of 8 is equal to 3, and that's because 2 to the third power equals 8. Log base 2 of 4 is equal to 2 because 2 to the second power is equal to 4. If we look back at our graph that we did when x was equal to 1, we saw that our y value was 0, so that was our x-intercept. And then looking at the first point that we plotted, when x was equal to 1/4, our y value was -2. All right, what's interesting is the next two x values that were asked for on the table. The next one is, what is the y value when x is equal to 0? Well, we sort of already talked about this. We saw that we had an asymptote sitting on top of the x value of 0, and the current can never touch or cross over that. So we don't have one. It's not possible for x to be 0. And the other x value it's asking about is -5. That's way over here, and our graph doesn't go anywhere near that because it's not crossing the y-axis. So it's not possible to have a y value either when x is -5. If you try to evaluate a log, finding the log of 0 or finding the log of a negative, you would end up getting an error. So it's not possible, I'm going to say not possible down here, or it's undefined to take the log of 0 or to take the log of a negative. And even if we think about this one over here, like for the answer of 0, we can't have 2 raised up to something and have it equal 0 ever. That would just never happen. We talked about this already, so that was just looking at the graph being reflected over the line y equals x. We had a reflection over this line. And then we also talked about number 6 already, that all of our x's and y's are switched. So the domain and range switched. We saw the equation for the asymptote switched. If we want to put something in here, we can just say, again, all of our x's and y's are switched. All right, so we're going to continue here with our quick notes and our learning targets for today. So I forgot to read these to you at the start. But the first one was to graph log functions and identify the y-intercept in the asymptote. We also wanted to identify the domain and range of a log function. So let's start with that. I'm going to actually divide our space into 2 sections. I'm going to leave a little bit more space though on the right-hand side. So learning target 1 and 2 was just all about the graph of a log function. All right, so we're going to make a little sketch here off to the side of what we saw this graph look like, mostly just giving ourselves room on the right side of the y-axis. We saw that our line, our graph, doesn't exist on the left side of the y-axis. And we saw that the log function had a y-intercept of 1, 0. I'm sorry, not a y-intercept. It had an x-intercept of 1, 0. That was our x-intercept. And it passes through that point. It goes onward and upward and has a little bit of a curve to it as we move to the right. And then it's getting closer to the y-axis and it gets very vertical as it goes to the left. But it's never going to actually touch or cross over the y-axis because of this asymptote line. So let's go ahead and draw in that vertical dotted line. All right, so a few characteristics about this function. So again, starting with our x-intercept, it was at 1, 0. The asymptote equation, now we have a vertical line, so it was x equals 0. The domain is referring to the x's that are being used in the function. We see that the x's used are only positive numbers. So we saw that our domain was just all real numbers greater than 0, which is another way to say that they're all positive. And then the range is asking about what are the y values that are used. So if we look in this vertical direction, the y values that are used is all of them. We have all the positive y values that this graph is spanning through. We have all the negative y values. So our range, describing all the y values that are used, was all real numbers. All right, what we saved the other section for, the last learning target we had for today, was to be able to describe a log function as the inverse of an exponential function. So we saw a lot of interesting connections here on the log graph being the inverse of the exponential graph. All right, so what I'm going to draw here again is going to be a sketch of an xy axis. And I'm actually going to think about putting both of the curves on the same picture. So starting with an exponential curve. So an exponential curve looks like this top graph. And then putting the graph of the logarithm on the same picture, that one we saw looks something like this. All right, so one interesting thing was that our graphs were reflected over the line, y equals x. So I'm going to have us draw that in again on this picture. And we're going to make a note of that off to the side here. So this is because exponentials and logs are inverse functions. The graphs are reflected over the line y equals x. Another thing that we saw is that if we have a point on the exponential graph, so I'm just going to pick a point here and I'm going to label it as A, comma, B. That point AB is going to map to a point over here on the log function where the x and y value positions are going to switch. So it would map to the point B, comma, A. We're just switching the order. So let's make a note of that here. Each point, AB, on the exponential graph is mapped to the point BA on the log graph. So the other interesting thing about this process is you can do this for any base. So we did this for 2 to the x. That inverse was log base 2 of x. We figured out a table for 2 to the x. We switched the x and y to get log base 2. You could have started with 3 to the x. So you could have done a base of 3 for your exponential y equals 3 to the x. Again, we could do a table to get some ordered pairs. When you switch those, it would be log base 3 of x. For the exponential, you could have done 5 to the x. And the inverse would be log base 5 of x. So whatever is the base that's holding up the exponent in the original exponential equation, keep that base the same, log base whatever, it's that little number down at the bottom, that's the one that it's connected with. That is the inverse. And so it's wanting us to graph this equation. We want to identify at least 4 points on the graph. And then we're going to do the intercept, the domain, the range, and the asymptote. So starting to think about there being a different base, log base 3 of x, it's going to be the inverse of 3 to the x. So before I even start to think about log base 3 of x, I actually like to start by just making a table of values for the exponential. So let's do it for 3 to the x. And it's good to get some negatives. We'll do a negative x value, we'll do -1, we'll do x is 0, x is 1, x is 2. Remember, the domain for an exponential is all real numbers, so any type of x value can be plugged into this one. If we do 3 to the -1, that's equal to 1/3. 3 to the 0, anything to the 0 is 1. 3 to the first power is 3, and then 3 to the second power is 9. So we don't actually need to graph 3 to the x. You could, but I think it's helpful to just get the values in the table. And then I like to think about, okay, so what's going to be the table when we do the inverse? So now that we're trying to do log base 3, all of these are going to switch. So instead of it being -1, 1/3, it's going to be 1/3, -1. We're going to switch the next set, 1, 0. We get 3, 1, and we get 9, 2. That's the inverse. Inverse is all about switching x and y. So now the only points that I'm going to plot are the second set that we did, and that's for log base 3 of x. So I'm just going to estimate here when x is 1/3, it's like 1/3 of the way, y is -1. So this is my first point. I still have the point 1, 0. That's my x-intercept. Now I have the point 3, 1. And then all the way over here I get the point 9, 2. So sure enough, we have identified 4 points. We'll go ahead and connect it like this. Make sure that that tail is very vertical looking. It's not going to cross over the y-axis. I'm still going to put in my asymptote here as a dotted line. It's still in the same place on top of x equals 0. Okay, so we had a little bit of help here on the graph. Take a moment here on your own. So using that graph, go ahead and fill in the 4 questions off to the side. All right, so these are actually no different from what we did for log base 2 of x. We still have an x-intercept at 1, 0. The domain is still only positive values for x. The range is still all real numbers, and the asymptote is still a vertical line that goes through x equals 0. Okay, the interesting thing on this question, in part B, we're now going to do a transformation of log base 3 of x. So rather than having the most basic version of that equation, we have a few changes to it. So notice that we have a 2 added out in front. Move this off to the side. And then we have log base 3, so we know it's based on the log base 3 that we did above. But now it's not just x. Now in parentheses we have an x minus 4. So the first thing we're going to list out here are the transformations. That means how is it changing? Is it moving up, down, left, or right? So when we take a look at each part here, let's just look at the 2 that's being added in the front. This is the same as adding 2 on the end. It actually doesn't matter if it's added on the very front or if it's added on the end. Normally, what happens when we add something onto the end? of a function, what direction does it go? Up, down, left, or right? Tell your table, what direction is it going to go if we add 2? All right, nice job. It's going to go up that many spaces. If you were subtracting a number on the end, or technically if you had a negative number being added at the front, that would be the same thing as subtracting a number on the end. That's going to move it down. So adding or subtracting on the outside, we know is always going to move up or down. All right, let's look at the next part here. So here we are subtracting 4, but it's inside the function. We know it's on the inside because of the parentheses. So that means it's going to go left or right. I want you to tell your table which one is it. If we're subtracting, is it left or is it right? Okay, it is right. We're going to go right 4 spaces. If we were adding a number on the inside, we go to the left. Remember, the left-right, it's always a little weird. It's opposite the direction you think it would go. So if we're subtracting on the inside, it's going to move everything to the right. Okay, just to put another example off to the side, if it was log base 3 of x plus 4 in parentheses, and then it had like a minus 2 on the end, just to give an example that is the opposite of what we did, this would go to the left 4 spaces, and it would go down 2 spaces. So we've kind of seen an example here of all 4 directions that this can go. Okay, so what we're going to do here on the graph, so we're going to graph this one on top of the one that we did before. What happens on the log graph, anytime you're moving left or right, everything moves, even the asymptote. So the asymptote that used to be here, well, now it's going to the right 4 spaces. So I'm going to draw the new asymptote is passing through the x value of 4. And then every single one of these points is going to go to the right 4 spaces and up 2 spaces. So starting here, I'm going to go right 4, and then I'm going to go up 2. I'm going to do the same thing here at the next point. Right 4, up 2. This point here is going to go to the right 4 spaces, up 2. This one might go a little bit off, because it's going to go to the right 4 spaces, up 2, so it's going to be somewhere like this. So the transformed graph is going to be the one here on blue. Always move your asymptote over first before you connect the points, because you don't want that vertical tail to accidentally cross over the asymptote when it is not supposed to. So down below, when it's asking for the transformed intercept, it's going to be asking, like, this used to be the intercept. When that went right 4 spaces up 2, it turned into this. So the transformed intercept is now at the point 5, 2. It's actually not an intercept anymore at all, because it's not going through an x-axis or y-axis. Now, the domain is only all real numbers greater than 4. Because the asymptote shifted over 4 spaces to the right, we cannot have an x value that's any less than 4. So it's only x values greater than 4. The range has not changed. The range is still all real numbers. So seeing that again real quick on the graph, domain is now greater than 4. The asymptote is x equals 4. The range, however, does not change.